This is the Trucks and Corners worksheet from the first lesson of the cornering unit for reSolve. First of all, we've cut out the car, cut out the van and cut out the truck, and now we're going to see how they drive around this corner. Now the car is much thinner, of course, than the lane, and it easily goes round. I don't have any trouble getting the car around the route, around our corner. Let's try the van now. The van is much wider. In fact, it's nearly as wide as the lane. Let's see how it goes. So driving the van along, and we're starting to have to bend here. It looks as if it's just fitting in the lane, perhaps. Maybe yes, maybe no, and then off he goes. So the van, although it was nearly as wide as the lane, it nearly managed to get around the corner. Let's just try the truck. Here you go. The truck's very long. This is how long it is. So let's just see how the truck goes. It's not nearly as wide as the lane. So let's see driving around. But as soon as we start to bend here, you can see that the truck comes out of its lane, and at times it comes out quite a long way. And then straightening up, and off it goes. So we see that it seems to be the length of the truck is more important than the width of this van for cornering, going around this corner. This is the first mathematical model. It shows a scooter going around where the angles have been turned by a fixed amount. So in this case, here we have the model here. This is our little scooter. This is the front wheel and this is the back wheel. I've set the wheelbase to 1.2 metres. Long for a scooter, I understand, but it gives us a larger image. The wheel turns 30, and we're going to move the scooter using this button. You can see here, this shows you the programming for the mathematical model here. Students don't need to use that, and they really only need to use this version here, this window here. I have downloaded this software to my computer, and it's using GeoGebra Classic. Oh, goodness me, I didn't mean to do that. Put him back. Put the scooter back. Okay, let's move the scooter. Here it goes. Now what you can see here is that the scooter is turning quite quickly. With the angle of the wheels is 30 degrees, and the green dots are the front wheel of the scooter, and the red dots are the back wheel. We can start to see that the front wheel is definitely moving in a circle with this constant angle, and the back wheel is following in a smaller circle. And we can, when we get round, we'll go to we should complete the circle. Now, we could just move it backwards a little bit to see what's happening. These dots are because this model is working with discrete increments. It's not continuous, but of course, in real life, it would be continuous. What we can also see from the model here is the front wheel path radius was 2.4. It's interesting that that's double the wheelbase, isn't it? Maybe we should look into that. Here's the rear wheel path radius at 2.8 metres, and that gives us a cut-in distance. So the difference in the radiuses of these two circles of 0.32. So let's say 32 centimetres. So we've definitely got a cut-in there. And if we want to set the sliders differently, we can move the scooter down to 0, so it goes back. We can change the wheel turn, for example, just like this. Oops, and we don't want to see that at the moment. We can change the wheelbase, making it bigger or smaller. This is how we can change the wheelbase actually. I've put at the minimum of 0.5, so 50 centimetres, and a maximum of 10.5, and that's so we can get a bike for 10 people around a corner. But students don't need to look at that, and then we can set the wheelbase as well, and we can we cleared this. Okay, so that's the scooter model version 1. This time I'm showing a file that's being used online from the GeoGebra website. You can see that there's not so much, there are not so many controls that students can use that are evident here. Now, what we've got here is, this is our bicycle here, and here we're going to model where the front wheel is driven around a circle, and we're going to see what happens to the rear wheel. Now, as it happened, so the front wheel is going to be in green, and we're really looking at what the rear wheel will do. So here we can move the front wheel and drive it around the circle. Now, what you see is that as the front wheel goes around the circle, the rear wheel travels around another circle, in fact, a smaller circle. So that what we've got here is a demonstration that the rear wheel will follow around a circle if the front wheel's going around in a circle, and we've also got a calculation that shows what the radius of the rear wheel path is, and then how much it cuts in by. So here I set the wheelbase to 3, really just 3, which at 3 meters would be very long for a bicycle, but it just gives me a good image here, and a front wheel radius, path radius to 6.5. So I could make it a bigger path radius, and there you see here there's our bicycle starting off. If it was a much larger circle, then the cut-in seems to be quite a lot smaller. Okay, here 44 centimetres, and of course we can also change the wheelbase. So if we change the wheelbase to make it a very large bicycle, that's it, or a very small bicycle, whatever we like. So this version is perhaps easier for students to use, but there's less control. This mathematical model shows a slightly more realistic version of the scooter. So this is a scooter with overhangs. We've got the front wheel there and the back wheel here, and then we've got a slider that determines where the end of the scooter is and where the front of the scooter is. So we can set the wheelbase here by moving the that one backwards and forwards. Back to 4, let's put it at 4 again. And then we can also set the overhang if we like. We can move it in, which 2 of course is quite unrealistic. Probably would be a lot less than that. You can see that the scooter gets much smaller, but in fact I'm just going to put it up to the maximum because we can see it more easily. Up we go. Good. And then to move, we've got a wheel turn set at 45 degrees at the moment, and as we move the scooter, we can see that the green circle, the front wheel has been turned to this angle, so that's determining this circle, that the outside, the very front of the circle goes much further out. And let's just have a look at what happens. Here's the back wheel, and this is the end of the scooter. So let's move it along a little bit further. And what we see is that, again, this one stays a long way, much further out. Here's the front wheel of the scooter, and the back wheel is the red, and the very rear of the scooter is this orange one, and it's further away from the centre of the turn than the back wheel is. So the back wheel, we can see, is the closest point to the centre of the rotation, and the front of the scooter is the furthest. This is the model that shows our first four-wheeled vehicle. And so we've made this one so that you'll be able to play around with the dimensions of the vehicle and see the full space that the vehicle goes over. Here we're thinking about this as around a roundabout, but of course you could also use this modelling a corner, say with just a quarter of the circle. So F here, this is the front wheel, and here's the back wheel. So this vehicle would have been heading in this direction, but now the wheels are turned at an angle. In this case, what we've done is just to have controls for the size of the body, so we can change the wheelbase, for example, making it smaller or larger. I've just set it there at 8 metres. We can change the path that the front wheel goes around. That's going to be the one that drives this vehicle. We can change the body width, so I can make it a wider vehicle or a smaller vehicle. So let's just, I think I had it, say, 2.5 metres. The front overhang makes the vehicle longer, so that's the distance between the front wheel and the front of the vehicle. And the rear overhang makes the vehicle longer or shorter, of course, at the back. So let's see what happens when we're travelling around this specified circle with a radius of about 14 metres. We can see that the really key things are that this outside corner is going to be the one that's furthest away. I think everybody intuitively understands that. And then we get the inside rear wheel is always closest to the centre. So this is the smallest circle. And you can see here that the overhang at the back really is very, very close to the path of the rear wheel. Let's make that a bit more extreme, and we'll see what happens there. So if that was where that was at the rear overhang, still this point, the back here, wouldn't come closer than that point. So this, where the wheel is the closest point to the centre on our model. And as we go around, you can see how it works. So I think this one gives students a good idea of the path that's covered by the vehicle. The fact that this point here is the one that's furthest from the centre, and this one is the one that's closest to the centre. If we want to do some experimentation to see how wide the lane needs to be, we can use these reported values to do some trial and error and see what's required for a roundabout. This mathematical model lets students experiment with driving a car into a parking space. The idea is that we're going to look at how wide the roads need to be between the two sets of parking spaces. And here we've got a picture of the parking spaces. You can see 3 cars, 1, 2, and 3 parked in there. And the idea is to park this car into there. We can set the specifications of the car, the wheelbase, the body width, the front and rear overhangs, and then we have to drive the car in. And we do that by setting the path radius for the front wheel, as we did before. So let's see. Oh, the edge of the access way is actually calculated from how much space the car needs to turn. And we'll just see how that happens in a moment. So let's move the front wheel. So the car's coming in. You can see that the access way would have been wide enough there. We'd have missed. And as we come here close, you can see that the front outside of the car is just going into the next person's car parking spot, which may well be okay, depending on the size of their car. And we can see that the rear wheel up here will just skim. So that would give us an idea that this would probably just about be okay. And for that, this is the access width that we need, 6.24 metres in this case.